In the lecture on the physics of sound, I talked about a microphone. In this lecture, I'll explain how microphones, speakers, and our ears work to detect or generate sound. At its simplest, a microphone is a sensor which converts sound into an electrical signal. The microphone reads changes in air pressure through a membrane. Imagine blowing up and deflating a balloon. The change in air pressure creates physical movement. The first truly practical microphone was invented in 1923, and the basic design of the moving coil microphone has not changed much since. There are many types of microphones, but the most basic and robust is the dynamic microphone. In a dynamic microphone, the membrane is connected to an induction coil, which is positioned in a magnetic field. As the membrane reacts to changes in air pressure, it moves the coil of wire back and forth in the magnetic field, which produces electricity. Together, the magnet and coil of wire are called a transducer. A transducer is a device that converts signals from one form of energy to another. Types of energy include thermal, chemical, electromagnetic, or mechanical. In this case, the membrane takes mechanical energy and changes it into electrical energy. Once the changes in air pressure are converted to electrical energy, they must go into an analog to digital converter for the computer to read the information as zeros and ones. I'll go into more detail about the ADC when I discuss analog versus digital signal in a later lecture. A speaker is essentially a microphone in reverse. Some headphones can actually be plugged into a microphone input and used to record audio. The quality isn't very good because the headphones aren't optimized to record sound, but the transmission works. The moving coil speaker was invented in 1898 and hasn't changed much since. So when a computer has an audio file, it must go through a digital analog converter, or DAC, to change the bits and bytes to electrical energy. Usually this electrical energy needs to go through an amplifier to increase the low power signal. This electrical signal then moves through a coil of wire surrounding a magnet. The changing electrical signal within the magnetic field creates a mechanical force which causes the coil to move. The coil is connected to a lightweight diaphragm or cone which moves back and forth, pushing and pulling atoms in the air and causing the changes in air pressure which create sound. So how do we hear this sound coming out of the speaker? First, our pinna, or the visible part of the ear, collects the sound and funnels it into the ear canal. Pinna are extremely important to our hearing. Changing the shape of the pinna changes how we hear. Sound travels down the ear canal until it hits the eardrum. The eardrum is a thin membrane which moves back and forth as the pressure changes, just like the membrane on the microphone or the speaker. The eardrum is then connected to 3 ossicles, the smallest bones in the human body. These bones transmit the motion of the eardrum into the cochlea. The cochlea is a fluid-filled spiral with hair cells or cilia around the edges. These hair cells, properly called stereovilli, are the mechanico-sensing organisms of hair cells. They respond to fluid motion and change the mechanical stimuli into electrical stimuli or nerve impulses that our brain can understand. So the stereovilli are just like transducers. In essence, our ears function just like microphones. In fact, the inventor of the telephone, Alexander Graham Bell, recorded sound onto glass using a cadaver's ear as a microphone. He kept the pinna, eardrum, and ossicles intact and then attached a piece of straw to the other end of the bones. As the membrane moved in response to sound, the straw traced the pattern of the vibrations onto a moving charcoal-coated glass plate.